First, we're gonna do a little bit of a refresher in modular arithmetic. So what's arithmetic? Well, as you know, since elementary school, arithmetic are those four operations: adding, subtracting, multiplying, and the division. As you've probably learned in one of your math lectures and immediately forgotten, we can also do that modulo a number. So, taking a number modulo means just dividing it and just looking at the remainder. So, if we take a number and 30 modulo another number, here 7, well, whatever comes after the modulo is usually called the modulus. So, take this number modulo 7. 30 modulo 7 is 2, because if we divide 30 by 7, we get 4, the remainder of 2. And working modulo a number always just looks at the remainder. So, to put it in other words, regarding the modulos 7, 2 is in an equivalent class with every number that's also has a remainder of 2 after being divided by 7. Okay, so that's what we call a congruence. Two numbers are congruent to one another if they differ by a multiple of the modulus. So, in this case, 30 mod 7 is 2. 44 modulo 7 is also 2. So, these three numbers here, 30, 44, 2, are congruent modulo 7. That means when we calculate anything modulo 7, these are equivalent. We can just switch the numbers and we will have the same result. So now we can start with calculating. Well, can multiply. Straightforward, we multiply two numbers. And then we take it modulo, we get a result. We can here in this example take the 19 times 37 mod 7 is 3. But of course we can also reduce those numbers and take them individually. Mod 7. So 19 mod 7 is 5. 37 mod 7 is 2. So we can also just calculate 5 times 2, which is 3 modulo 7. So the same as those big numbers. Here on the right side I've included the Python code so you can check for yourself. Okay, now division works quite similar but a little bit different than what you've learned in elementary school. So here we want to divide 3 by 4 mod 7. I'll rewrite that in this notation that you probably know. 3 times 4 to the power of minus 1. So 4 to the power of minus 1 is the multiplicative inverse of 4. And in regarding modulo 7, the multiplicative inverse of 4 is 2. You can check that by just calculating. 4 times 2 has to be 1 mod 7. Why is that? Because, as you probably learned in your math lecture and then forgotten, if you associate an element of a group with its inverse, you have to get the neutral element. Neutral element regarding multiplication is 1, obviously, so here 4 times 2 would be 8, modulo 7 is 1, so 2 is the multiplicative inverse of 4. So instead of calculating 3 divided by 4, we actually calculate 3 times 2, mod 7, which is 6. So 6 is the result of 3 divided by 4 when we work modulo 7. This multiplicative inverse exists for every number a that is coprime to m. And now we have everything we need to solve equations, modular number. So, just as you have learned in school, you can solve for x. Just when it comes to division, you have to calculate the multiplicative inverse. This calculation of the multiplicative inverse is, you can do that efficiently over every prime number. The functions that do that in most programming languages are either called XGCD, extended greatest common divisor, or extended Euclidean algorithm, or just invert. And in Python, since Python 3.8 actually, you can also use the built-in power function, po, by using an exponent of -1 and a modulus. Okay, so to express this a little bit more mathematically, what we have done with our little Python snippets working modulo n is we've actually worked in the ring of integers modulo n. Usually this is the notation for it. That just means we just work with the numbers 0 to 6 modulo 7 in this case. But you have to remember these numbers here are actually equivalence classes. So this 2 here stands for all numbers that are congruent to 2. So it also stand for 9, for example, for 16, 23, and so on. Just all numbers that modulo 7 are 2. So all numbers that are congruent to 2. I'm showing you that because in the paper you might stumble across this notation. I don't want it to confuse you. Well, actually, this ring is not only a ring, since 7 is a prime number, and we have said that inverses exist if the element is coprime to the modulus. Well, 7 is a prime number. Everything is coprime to the prime number. This is a prime number. So this is not only a ring, this is actually a field. Fields are usually denoted like that. So finite field F7 has the same rules as above. It just means that every element has an inverse. So we can divide by every element in this. Yeah. So ring, if you remember, consists of a set and 2 operations, addition and multiplication. And the inverse of addition is subtraction, and the inverse of multiplication is division. The difference between a ring and a field is that in a ring you don't need to be able to divide by every element. That is because not every element has an inverse. Well, in a field you can do that.